Okay, so let's unpack this a bit. Imagine a strategic asset, right? Designs way back in the Cold War. From what a lot of people might just dismiss as some kind of analog era. Imagine that asset not just sticking around, but actually dominating today in our super digital 2025. That's what we're diving into today. The Northrop Grumman B-2 Spirit, the strategic bomber. And the really surprising thing, the core question is, how? How can an aircraft thought up decades ago still be the absolute top-tier platform, able to get into the most heavily defended airspace anywhere? Like, think modern air defenses, maybe Iran, hypothetically. It kind of challenges that common idea that it's just some old analog relic, because it's not. We're going to show you how it was actually a pioneering digital machine. Its whole revolutionary shape was only possible because of a huge leap in computer tech. So our mission today, uncover the tech, the challenges they face building it, and the strategic reasons it's still unmatched. You're basically going to get the inside track, get really well informed on this incredible aircraft.
Yeah, it really was a fundamental shift in thinking, military thinking. For decades, the idea for bombers like the B-1A, the B-52, it was just higher and faster. Simple as that. But the B-2, it completely flipped that. The focus became radically different: invisibility and precision. And this wasn't just some random idea. It was driven by a real urgent need. These increasingly complex integrated air defense networks were popping up. And the absolute key to making this whole invisibility thing work, it was computer technology. Nascent, sure, but powerful. That ability it still has to get into these modern A2AD zones, these anti-accessory denial bubbles. No other aircraft can really do that today.
Right. So let's set that scene. How did this need for invisibility become so critical? By the mid-70s, the U.S. Air Force looked around and had this stark realization. Their current bombers, even the B-1A, which was pretty new then, and definitely the old B-52s, they were becoming really vulnerable. Soviet radar, Soviet SAMs, surface-to-air missiles. They were getting too good. Speed and altitude just weren't the protection they used to be, not enough. So suddenly there's this urgent demand. We need a new bomber where stealth isn't just a nice to have, it's the defining thing. And this is where you see the big gamble, right? President Carter canceling the B-1A. It wasn't just about money. It was a huge strategic pivot. Betting the farm on this advanced technology bomber program, the ATB. Way more ambitious tech, way riskier, but potentially much more survivable. They picked revolution over just tweaking the old formula.
And the groundwork for that bet, that gamble, it was laid in secret in the Black World programs. Starting around 74, DARPA, the Defense Advanced Research Projects Agency, they started digging deep, looking into aircraft structures that could, seriously deflect radar waves or even absorb them. This led to projects like Have Blue, experimental survivability test bed. That's where Lockheed came up with their famous faceted shapes. Those sharp angles weren't random. They were calculated using early computer models, trying to figure out how radar bounces off flat surfaces. At the same time, Northrop had its own secret project, Tacit Blue. They were exploring different ideas, curved surfaces, fly-by-wire controls, using these new composite materials. And these programs worked. They proved, basically, that a long-range stealth bomber wasn't just science fiction. It was possible, and here's the crucial point, the aha moment maybe, without the computers. Forget it. The math needed to figure out radar reflections to get those shapes just right. It was incredibly complex, impossible without computers. So this idea of the B-2 being analog era, it's just wrong. Digital simulation was baked in from the very start of stealth. And it's interesting, you had this quiet tech race inside the U.S. too, Lockheed's facets, partly a result of 70s computer limits. Northrop wanted those smooth curves, but that needed the kind of supercomputing power that only really showed up in the 80s. That processing power unlocked the B-2's design.
And Northrop had history on their side, didn't they? This wasn't their first flying wing. They'd been experimenting with flying wings way, way back. The N9M, the YB-49, back in the 1940s. And the flying wing itself is inherently stealthy, right? Just the shape. No vertical tail sticking up, no obvious fuselage separate from the wings. That alone massively cuts down the radar signature. But wait, if they had it in the 40s, why did it fail then? Stability problems, I remember reading. So why did it work in the 80s? What changed?
Digital fly-by-wire. That's the missing piece.
So Northrop's experience plus the new tech.
Exactly. Their history with flying wings, plus the stealth tech proven by Tacit Blue, they were the obvious choice for the ATB contract.
Which they won in October 81, and then years of secrecy, right? And saw the rollout.
Yep, November 22nd, 1988. They unveiled the first B-2, the Spirit.
And politically, this was huge. Reagan had campaigned using the B-1. The B-1B got brought back as sort of a stopgap. It really highlights how ambitious and maybe how risky everyone thought the B-2 project was. A real leap of faith.
So you achieved this incredible stealth, but what did you give up? What were the trade-offs? If you put the B-2 next to, say, the B-1B Lancer or the Russian Tu-160, the differences are stark. The B-2's whole reason for being is deep penetration using stealth. That unique shape, the RAM materials hiding the heat signature, everything serves that. And it flies fast, but subsonic. Mach 0.95, roughly. Now look at the B-1B or the Tu-160. They were built for speed, supersonic. Mach 1.25 for the B-1B, Mach 2.05 for the Tu-160. They carried weapons externally, prioritized speed, payload. Stealth was much less of a factor.
Different philosophies entirely.
Completely. And the B-2 was digital fly-by-wire from the get-go. The others started more traditional, though they got upgrades later. Payload 2. B-2 carries 40,000 pounds, all internally for stealth. The B-1B, 75,000 pounds. Tu-160, a massive 99,000 pounds.
Wow.
So, yeah, unmatched invisibility for the B-2, absolutely. But it consciously sacrificed raw speed and that initial sheer carrying capacity compared to its peers.
Okay, let's dig into how it achieves that near invisibility.
Yeah.
The tech itself, it starts with that shape, right? The flying wing, just getting rid of the fuselage, the tail. This shrinks the radar target immediately. And the surface isn't simple, is it? It's all these complex, wide curves.
The meticulously designed curves. The whole point is to scatter radar energy away anywhere but back to the radar dish that sent it.
And those edges, sharp leading edges. And the back edge has that jagged sawtooth pattern.
Exactly. All part of managing the radar reflection.
And get this, here's a fact that always amazes me. That shape, plus everything else. It can make the B-2 look like a small bird on radar, or even like a big bug, under the right conditions.
Yeah, it's incredible. It's less about deflecting and more about precisely managing the reflection, like shattering the radar's view. Every single curve, every angle is calculated to diffuse those incoming radar waves. It's a big step up from the F-117, the earlier stealth fighter, those flat panels, the facets.
Right, you said that was partly due to computing limits back then.
Exactly. The B-2's smooth, flowing curves needed much more sophisticated computer modeling. Computational fluid dynamics, electromagnetic modeling, stuff we mentioned earlier. That's what allowed for this more advanced, more effective stealth shape. But shape is only half the story? Maybe less than half. Material science is huge here. Something like 80% of the B-2 is made from advanced composites. Carbon fiber, graphite, fiberglass, titanium.
So the structure itself helps hide it.
Yes. The skin itself, that carbon graphite composite, it's designed to absorb radio wave energy. And then on top of that, you have layers of special coatings, radar absorbent materials, RAM, and that iron ball paint on the leading edges. You hear about that sometimes.
Does that do? Absorb radar too?
Absorbs it and converts it into heat. Tiny amounts of heat, but it means less energy reflects back. And the engineering challenge here was immense. You needed materials that were strong enough to build an airplane out of and had these special radar-absorbing properties, dual function.
That sounds incredibly difficult and expensive.
Extremely complex, extremely expensive, a massive undertaking.
Okay, so shape, materials. But you mentioned earlier the flying wing is inherently unstable. That seems like a pretty major problem.
It is. A flying wing, naturally, just wants to tumble out of the sky without a tail, providing stability.
So how did they solve it?
The solution was the digital fly-by-wire system, but not just any FBW. It's quadruple redundant.
Meaning 4 backups.
4 independent layers of backup, yeah. It's incredibly sophisticated. And here's the mind-bending part. The pilot doesn't fly the plane directly.
What do you mean?
The pilot's commands, stick inputs. They go to the computers first. And those computers are making hundreds of tiny adjustments every second. Moving the control surfaces, 11s, rudders on the wingtips, even adjusting engine thrust slightly, just to keep it stable.
Wow, so the computer's constantly flying the plane, basically.
Constantly. The pilots often don't even feel these microcorrections. Imagine designing a plane that's deliberately unstable because that shape is better for stealth.
And relying entirely on computers to make it flyable.
Precisely. That's what we call a controlled configured vehicle, or CCV. The shape is for stealth, not stability. The computers create the stability. It really was one of the first true software-defined aircraft. Its ability to fly is coded in software.
Which also means, if that system fails...
It's catastrophic. The 2008 crash tragically demonstrated that. A failure in the flight control data system led to loss of control. It underscores how absolutely critical that FBW system is. Now, to do its job, the B-2 needs to see where it's going, find targets, but without giving itself away. It has to see without being seen. Its main sensor is the ANAPQ-181 radar. It's a phased array system, and crucially, it's designed for low probability of intercept, LPI.
LPI, low probability of intercept. How does that work? How do you make a radar stealthy?
Well, it's clever. It jumps between frequencies very rapidly, uses really wide bandwidths, and transmits at very low power levels. All that makes it incredibly hard for an enemy's radar warning receiver, the thing that tells them they're being painted by radar, to even detect the B-2 signal.
Sneaky. And it does more than just look ahead.
Oh yeah, it's super versatile. Over 20 different modes. Terrain following, navigation, targeting. It does a lot. And it's been upgraded over the years too. Went from PISA, passive electronically scanned array, to the newer AESA technology, active electronically scanned array, better performance, more reliable.
And for navigation, it's not just relying on GPS, right?
Mm-hmm.
Especially these days with jamming concerns.
Definitely not. It integrates GPS, yes, but also has astro-inertial navigation.
Using the stars.
Seriously.
Seriously, like old school mariners, but automated. Provides a backup that can't be jammed. Plus, it has a defensive management system constantly scanning for threats. This multi-layered approach is vital for operating in 2025, where you just can't assume GPS will always be available or reliable.
So we've covered radar stealth, but you said it's multispectral, meaning it tries to hide from other things, too.
Exactly. Infrared, sound, even just being seen visually.
How do they hide the heat from those massive engines? The engines, those General Electric F-118s, are buried deep inside the wing structure. That helps mask the heat and muffle the sound right away. The air intakes are on top of the fuselage, making them harder to see from below.
And the exhaust, that must put out a lot of heat.
It does, but they manage it cleverly. The hot exhaust gas is mixed with cold bypass air before it leaves the aircraft, and it's vented out over the top surface of the wing through those distinctive V-shaped troughs.
Why over the top?
That helps the plume dissipate faster and shields the heat signature from infrared sensors looking up from the ground. Very smart.
And visually, it's just dark gray, right?
A specific non-reflective dark gray, yeah, designed to blend in with the sky at high altitudes.
So it's really a total package. Every little detail seems geared towards reducing its signature across the board.
Absolutely. Down to engine placement, exhaust shape. It makes it incredibly hard to find or track, even if you're not using radar. And just to give you a sense of the scale we're talking about here, some quick specs. Primary function, multi-role heavy stealth bomber. Contractor, Northrop Grumman, of course. Wingspan, get this, 172 feet. That's wider than a 747's wingspan.
Wow, I didn't realize it was that wide.
Yep. Length is about 69 feet, height 17 feet, max takeoff weight, over 336,000 pounds. Payload, we mentioned, 40,000 pounds, all internal.
And only 2 crew for all that.
Just 2. Pilot and mission commander, highly automated systems, speed, high subsonic, around Mach 0.95, unrefueled range, about 6,000 nautical miles, ceiling, 50,000 feet.
So what this all means for you listening is just the sheer scale, the complexity. It was an enormous engineering feat.
But building something that revolutionary, it wasn't easy. It was incredibly difficult. Northrop Grumman themselves said they basically had to invent everything anew.
Not just the plane, but how to build it.
Exactly. New tools, new software design labs, completely new composite materials, new 3D modeling systems. Everything had to be developed pretty much from scratch. And the manufacturing tolerances, they had to be incredibly tight. Any tiny imperfection could potentially compromise the stealth shape.
Like, how tight are we talking?
Extremely precise. Think about Boeing building those huge 65-foot outer wing sections. They were the biggest single composite aircraft parts ever made at that time. Required totally new manufacturing techniques. And predictably, maybe, Northrop Grumman really struggled to meet the specifications initially.
So delays, problems.
Significant delays, yes. And defects, quality control issues in the early deliveries. It was a massive manufacturing challenge.
And those challenges, that reinvention, it leads straight to the B-2's other big story, the cost. The billion-dollar ghost. It became famously the most expensive aircraft ever built.
Per unit, yes. When you factor in all the research and development costs, it came out to over $2 billion per plane.
$2 billion per plane. That's staggering.
The whole program cost just ballooned. Started around, what, $36 billion estimated? By 1988, it was closer to $43 billion. Ended up around $45 billion total.
And for you, the listener, the key thing is what happened next. That huge cost, plus the Cold War suddenly ending.
Right. Congress looked at the price tag, looked at the changing world, and slashed the order drastically.
From 132 planes originally planned.
Down to just 21. 20 operational bombers plus 1 test aircraft.
So that whole reinventing everything drove up the R&D cost.
Massively.
And then cutting the number of planes meant spreading those huge fixed costs over way fewer units.
Exactly, which made the per-plane costs skyrocket even more. It created this vicious cycle, fueled a lot of political opposition, and there's another cost, an ongoing one. The B-2 is sometimes called a fragile beast. That revolutionary performance. It comes with a huge maintenance tail, huge logistical burden.
Mostly because of those stealth coatings, the RAM.
That's a big part of it, yeah. Those materials need incredibly careful, constant, and expensive maintenance to keep working properly. Plus, the aircraft itself is sensitive to weather, humidity. It needs special climate-controlled hangars. Always.
Which makes deploying it tricky, doesn't it? If it needs its special garage.
Very tricky. Forward deployment is complex. If a B-2 has a technical issue and has to land somewhere away from its main base at Whiteman in Missouri, like that emergency landing in Hawaii not long ago, it becomes a major logistical challenge, getting the right environment, the right technicians, the right parts.
So the fleet is getting older, showing signs of that strain.
You could say that. It's an aircraft built for global reach, but in some ways it's tethered to its home base for long stretches because of these intense maintenance needs.
That was definitely a lesson learned for its successor, I bet.
A critical lesson, yes. Balancing capability with sustainability and operational flexibility.
But here's the really crucial part for understanding its relevance today, in 2025. It's not a museum piece. It's constantly being updated. There's a relentless mission of modernization happening. We're talking huge software upgrades. I read one project had over 300 software changes alone.
Massive software blocks, yeah.
Plus better satellite communications, BLOS, beyond line of sight comms, an improved defensive management system to help it survive.
That's right. There's actually a big contract, like $7 billion, with Northrop Grumman running through 2029 just for these kinds of upgrades.
So this is the key, right? It's basic physics, the shape, the materials, they still work because physics doesn't change much.
The fundamental stealth principles are sound.
But its digital spirit, the avionics, the software, the sensors, that part is constantly evolving.
Exactly. Because it was built with that sophisticated digital architecture from the start, it can be upgraded. You can plug in new comms gear, update threat libraries, integrate new weapons, usually through software and modular hardware changes. That's its enduring strength. And that enduring strength translates directly into its unique role as an A2AD breaker, anti-accessory denial. It still has that unmatched ability to get inside the toughest, most layered enemy air defenses on the planet.
So strategically, it's the go-to tool for day one of a conflict against a serious opponent.
It's a primary option, yes. Designed to take out the high-value targets, especially the enemy's most advanced air defense systems, like maybe NUS-400, punching holes so that other, less stealthy aircraft can operate more safely.
You hear it mentioned in hypothetical scenarios, like striking hardened targets in Iran or North Korea.
Because it's uniquely suited for those missions, or even as a strategic decoy, potentially.
How does its stealth help against something like an S-400? Isn't that system supposed to be very advanced?
It is. But the B-2's stealth works across a broad spectrum, not just one radar frequency, and it operates very high. It makes it incredibly difficult for even integrated air defense systems, which link multiple sensors, to get a solid track and engage effectively. It's not really about being truly invisible, more about shrinking the detection range so much.
That it can fly past before they can react.
Essentially, yes. Before they can get a reliable firing solution and launch, it exploits that reaction time gap.
And it's not just about getting there. It's about what it carries when it arrives. The payload is pretty unique too, isn't it?
Very unique in one specific way. It's the only U.S. aircraft certified to carry the GBU-57, the Massive Ordnance Penetrator, or MOP.
That's the giant buster bomb, right?
The giant one, 30,000 pounds. Designed specifically for hitting deeply buried, hardened targets. And the B-2 can carry 2 of them.
2? Wow.
So that combination stealth delivery deep inside enemy territory, plus the ability to hit targets buried deep underground, is unmatched.
And it still has its nuclear role, too, part of the triad.
Absolutely. Still a critical part of the nuclear triad, capable of carrying B-61 and B-83 nuclear bombs.
So for you listening, what this means is that blend of stealth access and unique weapon capability gives the U.S. a strategic deterrent option no other country has. Indispensable for certain high-stakes scenarios.
Which leads us nicely into its legacy and what comes next. The B-21 Raider. The B-21 is explicitly the B-2's successor, and you can see the B-2's influence all over its design. Same basic flying wing shape.
But there are key differences driven by the B-2 experience.
Definitely. Key lessons learned. The B-21 is smaller. It's designed to be significantly more affordable both to buy and to operate. And crucially, the plan is for at least 100 of them, not just 20, learning directly from the B-2's small fleet size, which limits operational flexibility.
And the stealth tech itself, presumably even better.
Supposedly even more advanced stealth, and importantly, more durable ram coatings. The goal is no more need for those special climate-controlled hangars. That's huge for deployability. Plus, it's being built from the ground up with a modern open systems architecture. Makes upgrades much easier and cheaper down the line.
So the B-2 was both the blueprint and kind of a cautionary tale.
That's a good way to put it. Its successes, proving the stealthy flying wing concept works, were immense. But its challenges, the cost, the small numbers, the maintenance, provided equally important lessons. The B-21 aims to take the B-2's unique penetration capability and wrap it in a package that's more sustainable, more affordable, and much more flexible to operate.
So wrapping up our deep dive here, the B-2 spirit. Its staying power isn't some fluke, is it? It's not a contradiction that this Cold War design is still so dominant. It seems like the logical result of some really visionary thinking back then. It boils down to maybe two key things working together. First, that timeless physical design. The flying wing shape, it's based on physics, right? And physics doesn't really go out of style, so it stays effective against radar, a lasting advantage.
The fundamental principles hold up, yeah.
And second, that pioneering digital core. That fly-by-wire system wasn't just about making an unstable plane flyable.
No, it's the foundation.
It provided the backbone for all the upgrades, the adaptation.
Yeah.
It let the B-2 evolve as the threats evolved.
Exactly. So the B-2 isn't just some interesting historical artifact. It's really a vital bridge, a bridge to the next generation of stealth. It taught us so much about the technology, about the costs, about doctrine, lessons that are baked right into the B-21 Raider. And it's going to remain a potent symbol of American air power and a critical strategic tool for years to come, even as the B-21 starts entering service.
So, thinking about everything we've discussed, what's the one thing that really stands out to you from this deep dive? Maybe consider this. The B-2 kind of proves a principle, doesn't it? That if you have a truly fundamental innovation based on physics, like that stealth shape, and you combine it with a digital core that's designed to be adaptable, upgradable, you can create something that defies obsolescence for a very, very long time. Where else could that apply? Beyond military planes. That idea of a timeless physical design married to an evolving digital spirit, unlocking long-term, maybe unmatched capability. Something to think about until our next deep dive.